little bit behind where you're at in lecture, and that's because, like I said before, I think chapter 6 is the hardest chapter, and I really don't want to skip over the enthalpy, because that's what we really have yet to cover in here. I want to make sure that we spend some time with that and actually work through some of those harder problems. If we have some time at the end, we can start with the quantum number stuff, but that stuff typically goes pretty quick, and it isn't nearly as complex as enthalpy. So that's what we're going to be mainly focused on today, are enthalpy and the different types of it. So just a quick reminder on a couple of things. So the first thing is being able to recognize the different types of reactions that we have. So we have endothermic reactions. So these are going to be reactions that absorb heat from the surroundings. So with these types of questions, so if you see a conceptual question that has to deal with endothermic processes, one of the questions that they might ask you is what happens to the temperature of the system and what happens to the temperature of the surroundings. So you just need to be able to interpret what that definition means. Energy flow. The system is taking in heat, so the system is increasing in temperature. And the surroundings are going to get cooler because the surroundings are giving energy to our system to allow that to happen. Some examples of that, so endothermic processes. Now there's not a lot that you guys are really going to know, but an example would be something like photosynthesis, where energy is listed as a reactant. A more practical example would be something like a phase change. So this would be something that you would probably be more likely to see. So if I think about something like ice melting, that would be a result of an endothermic process because our system has to get warmer in order for that ice to melt. So really anytime you're going from a solid to a liquid or a liquid to a gas, you're going to be taking in energy to allow that to happen. That means then that the other type of reactions are exothermic. And these are going to be reactions that give off heat. So essentially heat is a product. Again, the energy flow for exothermic reactions is pretty much the opposite of what we see here. So our system is going to be the one that's losing the heat, losing the energy. So our system is going to get cooler, and the surroundings then are going to gain that energy and get warm. Again, a couple of examples. So one that we're going to see in a little bit would be something like a combustion reaction. So those are well known to give off energy, which fits our definition here of exothermic reactions. Some other reactions, so we can think about the opposite of this one. So if we wanted to freeze water, so turn it into ice. That would also be exothermic, because in order for that to happen, in order for it to freeze, our water has to get cooler, which means that it has to give off heat to allow that to happen. So that's kind of the backbone of the other stuff that we're going to talk about, which is enthalpy. So very simply, enthalpy is just going to be a measure of the heat absorbed or lost by a chemical process. Now when we talk about enthalpy, we're usually not talking about enthalpy on its own. We're talking about enthalpy in terms of a delta H. So delta just meaning as the result of a process happening. So the first thing is being able to recognize when delta H is positive and when delta H is negative. So for endothermic reactions, is my delta H positive or negative? Should be positive. Yep, so that means delta H is greater than 0 in these cases. And then that means that exothermic then are going to have negative delta H. So delta H less than 0. We do want to know what these look like on energy diagrams as well. So I'm going to draw an example of both of these and show you kind of what you're looking at. So you want to know what it looks like and how to draw it for an endothermic and for an exothermic process. So they're both going to look as follows. So you're going to have energy on your y-axis, and then reaction progress or reaction coordinate or something like that on the x. Here I'll do reaction progress. You could almost think about it as time, so as you increase on the x, the reaction's proceeding. Same thing for this one here. I'm going to draw one example of what these could look like, but you really don't need to memorize this. You just need to think about what we talked about over there. So if we're doing an endothermic reaction, we're just going to be looking at the energy level of our starting materials, so our reactants, and then the energy level of my products. If I'm doing an endothermic reaction, that's going to be a reaction that absorbs heat, that absorbs energy. So I would expect then that my products are going to be higher in energy than what I started. And that's exactly what you see on these types of diagrams. So usually you do your reactants further to the left and then the products on the other side. So this would represent an endothermic process because my products are higher in energy than my reactants. If you were ever asked to find delta H on one of these diagrams, the delta H would be this distance here. So the difference in energy between my starting materials and then my products. Exothermic, same idea, but the opposite type of reaction. So these are going to be reactions that lose energy. So that means I would expect my products to be lower in energy than my reactants. So you can see a diagram that maybe looks something like this. My products are lower in energy because my reaction lost energy. And then we can also find delta H the same way. Delta H is just the distance in energy between the reactants and the products. So that's kind of a rough overview of enthalpy. So again, I don't want to spend too much time on that because you've seen it by now. I want to actually look at the different types of enthalpy. So there's some specific ones that you guys need to know. We'll write those in what we're talking about over here. So I'll start with the most generic one, which is just delta H for a reaction. I'm not actually going to provide a definition for this. So you'll know it's delta H for just a generic reaction if it doesn't fit into one of these other three categories that I'm talking about. And these next three that I'm going to list are important because these always have to be in terms of 1 mole of something. So the first one, for example, is enthalpy of formation. So enthalpy of formation is basically the reaction that is going to form 1 mole of a compound. So the 1 mole part here is very important. So it forms 1 mole of a compound from elements in their standard states. So let's think about an example. So let's kind of derive how we would write that reaction. So let's say I wanted to write the enthalpy of formation reaction for methanol. So if I want to write the equation for this, first need to look at the elements that I have present. So here I have carbon, I have hydrogen, and then I have oxygen. So those are going to be my 3 reactants, but we have to think about what their standard states are going to be. So really you're thinking about diatomic versus monoatomic. Now I put carbon in here specifically because this is one of the exceptions. You're going to see carbon listed as solid, or you might see this written as graphite. That is carbon's standard state, so be careful for that. So that would be one of our reactants. Another one would be oxygen. So again, remember oxygen's standard state is O2. And then the other element that we have here is hydrogen, which is also diatomic. So it would be H2. And again, that forms 1 mole of our methanol here. Now this is where you have to be careful because you also have to make sure that these reactions are balanced. And this one is not perfectly balanced the way that I gave it to you. Now what you want to make sure of is that when you're balancing it in reference to 1 mole of the product. You do not want to change the coefficient in front of this at all, which means that this is the first time in the class where we're going to have to start thinking about using fractions or other ways on the left-hand side to get that to work. So like I said, we need this written as 1 mole. So if we were to balance this, carbon is fine. We don't need to do anything there. We have 2 carbons on both sides. Oxygen here, I only have 1 on the right and 2 on the left. So again, I don't want to change anything on the right because it needs to be 1 mole of that. So what that means is I need to put a fraction in front of this. So if I do 1/2 in front of the O2, that will give me 1O, which equals what I have on the right. So again, this is where you want to start using fractions if you need to. And then hydrogen here, we have 2 H's on the left, 4 on the right. So I just put a 2 in front of that. And that's how you would write the reaction for the enthalpy of formation. So again, be very careful with that 1 mole. And there's a couple of other ones that we're going to have to be careful with that with as well. The next one is delta H of combustion. So this is basically going to be the enthalpy for a combustion reaction. So heat given off, more specific definition, heat given off by combusting 1 mole of a hydrocarbon. So again, there's one more after this I'm going to show, but I want to keep showing you where the 1 mole needs to be. So in the one that we just looked at, it's the thing that you're forming that needs to be 1 mole. Now combustion reactions, so I'll kind of just give you a generic example of what these reactions look like. Now what's variable is what your hydrocarbon is. So hydrocarbon is just a compound that has carbon and hydrogen in it. Sometimes you can have oxygen in it as well, but usually it's just going to be C and H. This X and Y can vary, so these can be different numbers depending on which compound that you have. But this is your hydrocarbon and this is the thing that you're combusting. That's important because it needs to be in reference of 1 mole of this compound here. So this is the thing that needs to be 1 mole. If you're writing a reaction, you want to keep that as 1 and then balance the other coefficients in reference to that. Now the good thing with the combustion reactions is the other reactant and the 2 products are always going to be the same. So it's always going to be your hydrocarbon plus O2 gives me H2O and CO2. So again, the other materials are always going to be these 3 compounds here. What's different between combustions is usually the starting material there. But again, the thing that you need to be 1 mole is the thing that you're doing the combustion. Finally, the last one, this one you probably will see a little bit less, but I still want to bring it up just to be safe. And that's going to be the delta H of solution. So if you want to make a solution from something, so this is basically going to be 1 mole of the thing that you're dissolving in solution. So for example, if I wanted to write an equation, that would be something like making an NaCl solution. These ones you know the equations for by now, so this should be a little bit easier. So if I write the delta H for solution reaction for NaCl, this is what it would look like, because this is the process that happens when I make a solution with this. The thing that you need to be 1 mole is this part here. So again, those are kind of probably the main ones that you're going to encounter in this class, and those are the places where you have to have it in reference to 1 mole. Now, I'll kind of give you a generic overview of how we can calculate delta H. So first we'll look at calculating with the enthalpy of formation values. So the generic reaction is going to look like this. And again, I'm going to have you do some practice with this in just a minute. But essentially what you're going to do is you're going to sum up the enthalpy of the products. And then you're going to subtract the sum of the enthalpy of the reactant. And then from there you can go on to do different things. So for this I'm not going to do an example of it just because I'm going to have you guys try some and we'll go through those ones together, and I'm hoping at this point you've done enough examples and you could at least try this. So the problems that I'm going to have you guys do, so if you had last week's worksheet, you can pull that out because that's where these are going to come from. If you don't, I'm going to project it on the doc cam so you'll be able to see it as well. The ones that I want you guys to do are 2, 3, and 4. These 3 questions here, and we'll go through these in a hint for 2, you need to write a combustion reaction for C2H2, because that's the hydrocarbon. going to start going through those ones. So 2 and 3 were a little bit more challenging. So number 2, to be honest, you probably wouldn't have to do all of this in one question, but there's a bunch of different useful parts that I wanted you to get out of this. So what it's asking us for is it's asking for the heat of combustion for the following reaction. So like I said, if we're talking about a heat of combustion, and like I said before, we're doing this for C2H2. So that's the thing that we're combusting, and we know what the rest of the reaction is. We just need to make sure that it's balanced. It's going to be always plus O2 gives us CO2 and H2O, but we need to make sure that we balance it accordingly. Now, I've been really emphasizing the fact that you want to keep this as 1 mole of the thing that you're combusting. Technically, you don't have to do that, but if you don't have this coefficient as 1, you're going to have to remember to divide it at the end, and that's where a lot of people forget to do that. So I think it's easier to just keep this as 1 when you're setting up the initial reaction. And then you want to balance all of the other coefficients in reference to that. So we get the following coefficients here. So now we have our balanced reaction for the combustion of C2H2. Now we need to calculate what the enthalpy is. And this is where we sum up the enthalpy of the products minus the enthalpy of the reactants. Okay. So we'll start with the product side. So we have CO2 and H2O. So first it's going to be 2 times the enthalpy of CO2, which they give us in the table. That's the negative 393.5. And again, that weird symbol that I wrote before is a sum. So we need to add that together with the enthalpy of the other product that we have, which is H2O. That's plus 1 H2O, which is negative 285.8. And that's the enthalpy of the products right there. Now we need to subtract the enthalpy of the reactants. So the first reactant that we have is C2H2. So we have the table value for that as well. You don't also need to put the 1s in here, but I'm doing that more so for completeness. That's 226.6. Now, there's 4 things in our reaction here, but they only gave us 3 of them. The reason why they didn't give you the other one is because elements in their standard state have a formation value of 0. So oxygen is an element in its standard states. That's why they didn't give it to you, because they're expecting that you know that it's 0. But I will put it in here for completeness anyways. Times 5/2 times 0, which is still just 0. But if we write out every single part of this, this is what you would get. And then from there, we can just type this into our calculator. And that gives us about negative 1299 kilojoules. And that's per 1 mole of C2H2. So that's how you would do the first one. The second one is also a little bit tricky, so it's asking us to calculate the heat released when 2 liters of chlorine gas with a density of 1.88 reacts with sodium metal. So this is kind of like a limiting reagent problem, but not really, because they already tell us what the limiting reagent is. The first place that I would start, and pretty much for any of these enthalpy problems, if you're not given the reaction, I would start by writing out what the reaction is. So here what they're giving us is they're giving us a formation value of NaCl. We talked about how to write those reactions before. So we're writing a reaction that forms 1 mole of NaCl. We can do that with the following reaction. So this would be that reaction here. Again, you didn't have to do it that way. Like, you could have done it 2 moles of NaCl so you had full coefficient, but then again, you'd have to remember to divide at the end. But either way, this is, I think, the easiest way to do it, because it's already in terms of 1 mole of NaCl. The other information that they give us is that basically for every 1 mole of this reaction, this is going to give off negative 411 kilojoules. So that means if we had 1 mole of sodium in excess chlorine, we would get negative 411. That means that if we had 1/2 mole of Cl2 in excess sodium, that would give off negative 411. In this problem particularly, we don't have exactly 1/2 mole. We need to figure out how much we have exactly. So to do that, we can use the volume that they give us, because chlorine is a gas. We're going to see that written as a volume. Then we need to use its density to get it to a mass. The density here is 1.88 grams per 1 liter. And then again, we want to get it to moles to kind of figure out how much heat is actually going to be given off. And for that, we need to use its molar mass. Again, you're using the molar mass for Cl2, so it's 70.9 in this case. So what this tells me then is that this is 0.053 moles of Cl2. So again, the way that we're conceptualizing this is like I said before. So if we had exactly 1/2 moles of Cl2 and excess sodium, we would get exactly this amount of heat. So we're almost treating this like a dimensional analysis problem. So we have exactly 0.053 moles of Cl2. And I know that from my reaction, I'm going to get negative 411 kilojoules for every 1/2 mole of Cl2. So that's essentially the conversion factor that I'm using. And this will give me negative 43.6. So that's how we would go about that one. So again, it's just kind of applying the ideas that we've talked about before. 4 is a little bit easier, so 4 is more of a conceptual problem, talking about what I talked about at the beginning. I realized that the last question of that actually got cut off, so if you don't have the actual worksheet, there's one extra part here that isn't shown on the board, but I'll still tell you how to do it. So question A is the reaction endo or exothermic. Here we just need to interpret the sign of delta H. In this case, delta H is less than 0, so it's exothermic. B, what happens to the temperature of the surroundings during the reaction? It's an exothermic reaction. It's giving off heat, which means the surroundings are increasing, so they're getting warmer. And then finally, the last question, the one that got cut off from up there, says draw an example energy diagram. So again, this wasn't a quantitative question. I just wanted to make sure that you had the reactants and products placed appropriately. So again, an exothermic process means that our product should be lower in energy than what we started with. So you should have something that looks like this, where your products are lower in energy than what you started with. So it just had to have that general shape. Any questions on any of these 3 questions here? Okay. So then there's one last part of chapter 6 that I want to talk about, which is going to be Hess's law. So this can be a little bit challenging as well. So I think the easiest way to talk about Hess's law is talk about it in terms of an actual example, because then it'll make sense why we actually need to do this. So let's say I have this reaction here. Now normally if you got a reaction, your first instinct would be to look up the formation values in your appendix and then figure it out the way that we did before. That doesn't always work because that doesn't mean that we will necessarily have the formation value for everything. So let's say we got this problem and let's assume that we didn't have this value. You might actually have this one in real life, but let's just assume that we don't. We can't calculate it. Well, then you have a problem because then you can't just sum up the products and sum up the reactants and subtract them from each other because you're not going to have one of those values. And this isn't an element in standard state, so it's not going to be 0 either. That, in this case, we need to use a different approach here. So let's say we also have the information that we have 2 known reactions that go to help form this. Right out here. So we don't have this value, but we know these 2 known reactions here are reactions that help form CO, and we have the enthalpy of those reactions. So we can use the fact that enthalpy is a state function, so it doesn't depend on the path that we get there. We only care about our initial and final values, which will give us delta H. So what we can do is if we can find a way to add these reactions together to give us this reaction, we can calculate the enthalpy that way. Now with these problems, these are a little bit tricky. There's a little bit more variability on how you can solve them. So there's a couple of different ways. I'll just show you how I would approach it, but it doesn't necessarily mean that you have to do it that way. So what I would do is I would just start it, kind of do one thing at a time. So if I look at the reaction, this top one here is the one that I'm trying to get to, because that's what we want to know the enthalpy for. So if I start with this top reaction, I see carbon as a solid here. Then I want to look at the two reactions that I have and see where carbon solid is. So in the reaction that we're trying to get to, carbon solid is on the left-hand side. So I'm going to pay attention to that as well. Now only one of these reactions has carbon solid. It's this first reaction here. It also has carbon solid on the same side, which means that we can actually kind of copy that reaction down exactly the way it's written. The coefficients are different. You always have the option to multiply these reactions by something. If they're on opposite sides, so for example, if carbon was on the opposite side, you can flip the reaction around. Now, if you make any changes to either of these two reactions here, so if you flip the reaction, so if you flip the reactants and products, you'll have the same number, but you will need to flip the sign. So a negative becomes a positive and vice versa. If you multiply this reaction by anything, you need to multiply that delta H value by that as well. Now in this case, we don't need to do that, at least for the first one, because carbon solid is on the same side. So I'm just going to copy that reaction down here. That's usually how she has it set up for you on quizzes and exams, where you have a little bit of a workspace there. So I'll just copy that value the way that it is. Now let's look at the other thing. So oxygen is a little bit trickier because I have oxygen in both of these reactions here. So we already know we're going to have to use both of them anyways. So that one's not really going to help us here. The other thing that we can look at though is our other product, which is CO. So this one only occurs in one of those two reactions. So here, CO is a product. This is the only reaction that has CO on it. But the difference here is CO is a product. Over here, CO is a reactant. So that means if I want to add these together, I need them to be on the same side. So what I need to do then is I need to flip this reaction around. So I'm going to make that change and I'm going to copy that down here. CO2 gas goes to carbon monoxide gas plus 1/2 O2. Again, you want to be keeping track of your changes to your delta H as you've done this as well. Now in both of these cases, we didn't multiply the reactions by anything, so we don't need to change the number, but we did flip this one around, so we need to account for that here. So again, the number stays, but you flip the sign, so this becomes positive 283 kilojoules here. Now sometimes this will work right off the bat after this step. Sometimes you might have to do a little bit more work to get things to cancel. How to check that is you want to add the left-hand sides of your reactions together and the right-hand sides together, and then see what you have. The goal, again, is to get this reaction that we have at the top. So let's add together the left side. So I have carbon solid plus O2 gas plus CO2 gas. On the right-hand side, I have CO2 gas plus CO gas plus 1/2 of O2. Now clearly as written, this does not equal the equation at the top, but we can also cancel some things out. So we can cancel out things that are the same on both sides, or if they don't exactly cancel each other out, we can at least move it to one side here. So the first thing that I see that I can cancel out is CO2. I have CO2 here and here. So I can take that out of both sides of this combined reaction, because I have 1 mole of CO2 on both sides. The other thing that I can condense a little bit here is the O2. So on the right, I have 1/2 mole of O2 here. Over here, I have exactly 1 mole. So what I can do is I can get rid of this completely, and then I can lower this by 1/2. And now, if I look at what's left over, I'm actually going to get the reaction that I wanted to begin with. So here I have carbon solid plus 1/2 O2. Gives me CO gas. That's the reaction that we wanted to know the enthalpy for. Now all we have to do in this last step here is, as long as you've been adjusting your delta H values as you go, we're just adding these two together. Because again, we added these reactions together to get this one. We're adding the enthalpies together as well. So here, the delta H for this reaction is negative 110. Any questions on how to do that at all? Like I said, I know these are a little bit trickier and there's a lot of different ways that you can go about it. I'm just showing you the way that worked best for me. So what I'll have you guys try is that last question, so that Hess's law question, question number 5. You might be able to get through it, you might not, but I will give you the answer, just in case you don't. So try number 5, it's the same type of question, get as far as you can get in these last few.
Calculate the enthalpy change for the following reaction using Hess's law.
Coefficients by something, like if I want to multiply these coefficients by 2, I would multiply this by 2. So those are the two changes that you could. Yeah, so if you wanted to flip this one around, you would flip this up. And then if you needed to multiply those coefficients by something, then you would multiply that positive by the right side. So I would look at the reaction that you're trying to get to. So for example, if you wanted to start with NH3, for example, I see this reaction has NH3. So how's that? They're on different sides. So that it's kind of cueing me, and then I might want to flip that. So then I flip the reaction so that it becomes positive 92.2. Yeah, exactly. Because the other part here is I only have 2 NH3 in this reaction. I have 4 in the one that I'm trying to get to. And that's the only thing that has NH3 in it. So that means a problem. So I'm going to give you the answer, so I'm not gonna kind of work this one all the way through like I did before, just because we don't have time to do all of that. But I will give you what you needed to change with the two reactions. So there's two reactions, and I'll also give you what those enthalpy values are as well as what the final answer is. So for the first one, you had to make two changes to it. So you had to reverse the reaction, and you also needed to multiply by 2. So the enthalpy that you should have had for that reaction after you've made those changes was 184.4. And then the second one, you didn't need to flip it, but you did need to multiply it by 6. So that changes the enthalpy value, multiplies it by 6, which is negative 1450.8. And then just like before, the final enthalpy for the overall reaction is you're just adding these two numbers together, which should give you negative 1266. So again, if you got that answer, good. If not, make sure you go back and look and see how we actually got to that reaction. So for today, that is where we're going to stop. Now we did finish chapter 6. Next week we'll do the quantum numbers and periodic trends. So that is meant to be only 1 week anyway, so we're actually right where we want to be.